Okay, my name is Itai. My background, my background is from did my PhD in the Technion in Applied Math, and afterwards I work about 10 years as a data science in various fields, in e-commerce, liquid biopsia, cyber of automobile, log files, and other stuff. Right now, I'm working for Trust AI. What is Trust AI? Trust AI is a startup that we're focusing of AI omitting, which means that we're analyzing the result of predictors, regressive science, regressor, and stuff like that. And we made sure that you don't get some kind of a potential problematic segment or problematic outliers, meaningful things in the AI. Right now, our main focus is the insurance business, and we're and this is what we're doing. If anyone of you feel that everything is got to paid any insurance, welcome to approach me. Approach me and let's go. Okay. So, hello from beautiful Haifa. It's 3 a.m. here, so it's not late, it's early. We are very early. Okay. Right now, I'm a senior data scientist at Trust AI. I did a PhD in applied math technion. And if you're interested in data science, algorithm, and somehow this connection, feel free to call me. This is my email. Go ahead. Okay. Let's start the lecture. What is multi-class problem? Well, everybody here, I think, is familiar with a binary classifier, which means that you're doing something. You either, like, let's say in cancer, you either have this cancer or you don't have this cancer. And trying to do something, either like if you're working in e-commerce, either you have the convergence or you don't have the convergence. Now we're realizing what happened if you don't care about a single product in the e-commerce. What happened if you're interested in a few cases? Just like, let's say in your website, there's pants, a shirt, and shoes. And you want to predict if the person interested in one field. It goes for cyber. Cyber is my joint work, Nathan Katz, because in many cases, you're not interested in just, is there a threat, or if a threat, you want to focus what kind of threat it might be. And in NLP, because you want to find the sentiment and stuff like that. So you might have more than one thing that you want to go. Robotics and IoT. Actually, I first got interested in this problem when I was consulting for an IoT firm. There's a grounding factories that ground nuts, coffee, sesame, you name it. And each time they want to make sure which kind of nuts or something you're ground. And usually the worker doesn't tell you the right kind in many cases. So I got that. And another issue is predictive maintenance. Let's say you're doing predictive maintenance for a big hospital and your MRI, and you need to bring the technician for your MRI, but the technician costs lots of money. So bringing the wrong technician or the technician with the wrong gear is not a good thing. So, okay. Another thing that were interesting, fairness. Like if say you're, for some reason, you're not fair for one of those classes. If there's weak segment, like those two, very important. Robustness of the classifier. If the classifier, for some reason, forget one of the classes or just deprise it, you want to be sure. And another thing, if you have a deprise section, it could be a very good start if you're interested in adversarial example. Okay. Before I go to details, I rather have question during the talk and not afterwards. And then I'm an Israeli, and I'm not sure how many of you familiar with Israeli, but we don't have any. But we don't have anything that call polite and anything like that. So it would be the best if anyone has any question, just go ahead, ask me. And I think it would be much better for both the listeners, for the one who asked, and for me, than questioning after the talk. I'll be happy to answer after the talk, but go ahead, ask me. Okay, so the one against all. What is the one against all approach? You're choosing one of your classes, and you choose one of your classes, and then you just let these classes to fight against the rest of the world. This can work out quite well if you know which kind of class is more favorite than the other. If you have a one bigger class, more likely, more, but usually you don't have. The second approach is just like Fight Club. It means everybody's get to fight everyone. And which means that every class you always collect, what's the chance that I predict the class I when it was the class J? Another approach is hierarchy. What do you mean hierarchy? We're kind of clustering the classes, the classes in groups, and each time you're asking yourself, are you in this cluster or not this cluster? And then you go to the subcluster, just like the slide here. A movie can be action, comedy, thriller. Comedy can be romantic, splantic, etc., etc. Another approach, which is very popular in the field of, oh, everything is okay, everybody's happy. Okay, another approach which could be very, is the field of computer vision, is that embedding. We assume that you can embed your problem for some kind of Euclidean space. And after you do that, all thing you need to do is a simple regression. This space can be one dimension, it could be k dimension, and but it means that there's some kind of a topological order of the classes. The main problem with this approach is doing embedding is hard. I don't know how many people you are doing embedding on regular base, but it's a hard problem. And like it's the same intuition of word to vec, and if you have lots of data and you have the right neural network, you're fine. Otherwise, you're screwed up. Okay. From this point, I assume that I don't know the prevalence, which means I don't know how many classes, the percentage of each class, and I might get an evenly shared classes, and I might get a dominant class, which in real life, it's more likely to have a dominant class than an even space. Another assumption that nobody tells me any hierarchy. I don't know that there's a two classes that I can cluster them together, and I don't know anything about that. Another thing that I don't know any embedding, which we talked earlier, why it's in many cases you don't know the embedding. And another instance that every instance is in only one class. Like you can't, like unlike computer vision, then you can have pictures that contain both dogs and a dog and a cat. We assume here that this is not the case. Okay, let's start with the binary cases. We'll do a recap about that, and then we'll go back to the multi-class. Okay, binary classes is, which means that you have only two classes. One class, let's say it's a positive, the other one is negative, and it's a nice start. And you probably know this slide. And type error 1 when a man is predicted as pregnant, which is obviously it's false positive, and the type error 2 is the false negative, where the doctor says to the pregnant woman that she's not pregnant. Okay. A confusion map. What is the confusion matrix? And this is a very basic, but it's important issue, is that I have a 2x2 matrix, and which is I have the true positive entry, the false positive entry, the false negative entry, and the total and the true negative. Okay, this is the confusion matrix. I hope all of you are familiar with that. If otherwise, take a few seconds and go over it. Okay. Data tend to be unbalanced. I was working in cancer diagnostic. Thank God, most people don't have cancer. If you're working in the fraud detection business, fraudsters are a very tiny minority. And if you're talking in cyberspace, most of the time everything is cool. No, and so things might be unbalanced, and unbalanced might mean that one class contain one instance for every 1,000 otherwise. So keep that in mind. Okay. Let's start. We have the recall, we have the AUC, the precision, the AUC rock, and we'll have a small recap on that. Okay. What is accuracy? Accuracy is the percentage that the real is equal to the predicted. And as we noticed that this concept might be a little bit misleading. If your prevalence is not trivial, accuracy might be problematic. We all study machine learning course, and there's a women's doctor issue, and about 98 of the natural birthers are a single baby. So if you construct a classifier that say that you will never get twins, you will get 98% accuracy. I don't think anyone wants that. Okay, so next we started the kind of having 4 more quantities, and you can approach those quantities in many different fashions. I like to approach it in the condition probability. Recall is the real positive given a predictive positive. Precision is a predictive positive given real positive. specificity is real negative given predictive negative, and the negative predicted value NPV is predicted negative and real gives. Till this point, everybody's happy. If someone is not happy, not with me, let me know. Okay, I'll take that as an yes. And Yaakov, I met Yaakov and he told me that he loves pandas. So I wrote everything in a pandas method. It's just like you having if you're having function accuracy, and you can do the masking in the pandas. You can do it by group by if you like that, and everybody's happy. It's another way to do it. Okay, let's go back to high school. Let's talk about means, averages. Arithmetic, it's called algebraic arithmetic means, just like the most simple average that you can think about. Just take two numbers and add them up and divide it by 2. The geometric mean is just to take the multiplication and take the square root. To make things easier, I assume that all those numbers are strictly positive, so you don't get a complex number. Okay. The F score, probably heard about that, is the harmonic mean of the recall and the precision. The harmonic mean is just 1 over the arithmetic mean of 1 over A and 1 over B. So this is the way I see the F score. Any questions?
Can you, at this point, can you, before it becomes too complicated, can you explain F1 score to people who don't do machine learning at all the time, like in simple words?
Okay, the main idea is that we want somehow to average the recall and the precision. What is the recall? The recall, let's go here. Another one. Recall is that if someone told you that you predicted positive, what is the chance that you are positive? And the precision is the vice versa. If you know if something is real. So basically you're taking some kind of average. The reason you want to say that this average, like this way it's one of the ways that you overcome the dominant class problem. Let's say in the fraudsters, you're interested in two quantities: the chance that there is a fraudster and you caught him, and you want somehow to divide it up by the fact that if you said that this is a fraudster, it really was, because in one hand you don't want any fraudster to be able to do his thing. In the other hand, you can't afford saying for every one that is a fraudster, nobody would be able to use Visa. So basically, we want somehow to average those two quantities. So F1 score is taking the harmonic means. And let's say, and why do we take the harmonic means and not the geometric or the algebraic? If any of you remember in calculus 1, you prove the mean inequality, which means that the harmonic means is less than the geometric and less than the arithmetic. So basically, if you're taking a very more conservative average, you're more likely to make something that would be more balanced between the recall precision, which means, and this is the F1 score. And other means that you can choose, it's the reason I entered the Helder average is that recently I read a few blogs that are using this technique, which means is generalizing the means. If p equals to 1, we're getting the arithmetic means. P equals to 0, we're getting the geometric means. -1, we're getting the harmonic. And I read a few blog posts and people that are using this Helder, which is back in 2001, which is, but they're starting using it in either in pooling for neural network, in averaging and stuff like that. So the next time you hear about the Helder's average or the p average, remember that I mentioned that. Another approach is the weighted mean. What does it mean? In the F score, I assume that you prefer the recurrent precision in the right fashion, but this is not the cases. Maybe your product tells you that that whatever you do, you're not allowed to find the fraud. You're not allowed to give fraud sisters, even if some of your customers will have inconvenient. Maybe it's vice versa. So you can play with the weight of each score. Okay. Now this is the interactive part. And what happened if I'm getting that my target predictor and my predictor, all of them are zeros? What would be my accuracy and what would be my F score according to scikit-learn? Since I'm not sure all of you, but most of you are data scientists, sooner or later you might run to some kind of unit test. And let's say you're using the F score and you want to see what happened when you're getting 0 vector. So I'll take 1 minute. Yeah. Is it okay to let you 1 minute to think about that, and then I'll give you the answer?
Might want to show them the definitions.
Okay, maybe let's go to the definitions. Recall is the when you were giving predicted positive, which never happens here, and precision that you give real positive, which never happens here either. So, and the F score is averaging those up. So what would be the accuracy and what would be the F score? Actually, you can use it as in a job interview question. So if someone if someone claims that he knows all about scikit-learn, ask it. It's a little bit okay. Can I answer? So the question is the accuracy will trivially will be 1, but the F score, and this is the most interesting thing, would be 0. And this is a slightly surprising result. If any one of you is doing a test for a classifier, you should know that. Okay, let's continue. One can, well, there's a problem till now that we were only focusing on the positive. One might argue that there's no point of focusing only on the positive. We can focus on the negative as well, and you can do it in scikit-learn. There's the option of taking the negative, and which is the chance that if you were kind of averaging between if you were given a negative predicted and what is the chance it would be negative, and vice versa. If you said it's negative, what is the chance it would be negative? Okay, another, and this is I think one of the most interesting result is the Matthew correlation coefficient, which if we consider this matrix, G is the geometric average of the geometric average, and we're taking coefficient average of those four quantities. And if we take the determinant, we're getting the Matthews coefficient. And okay, let's see, what does it mean? What does it mean determinant? And let's go back to the geometry. And if one of the things I think it's a very good idea for all of you is when you say determinant, think about an 2 by 2, think about an area. And another interesting point of the Matthew correlation is that if you consider your positive to be 1 and your negative 0, the Matthew correlation would be the Pearson correlation of those two vectors. So this is a nice, interesting. And so basically right now we're detecting, if you're interested in collaboration, like, which means you want to know the probability from the classifier, you want to trace back the probabilities, a little bit calculus, algebra, and some basic probability could help you to construct this, and with those information. Okay, another classifier is the AUC, raw curve, and I don't want to go that because it's a little bit out of our scope, but we can play with the proba of being positive and negative, and then we can construct this curve. The area under the curve can give you us a good approximation how good are we doing. Okay, let's continue. Let's go to the multi-class finally. We want to anyone is not happy that I switched to the multi-class? Want to ask me anything about the binary case? Okay, I'll take this instead. Yeah, people in Austin are not that happy, or they're happy and we can continue. Okay, basically, so the Matthew correlation is correlation that you might think about that as the let's go back here. Let's go that you can do it, you can see it in two fashions, I think. First of all, we can say it is that it's the correlations mean that if the predicted and the real are highly correlated. What does it mean? It means that you did a very good job. It means that each time someone you said that it was 1 or 0, it was very likely to be 1 or 0. So congratulations, you did a very good job in this if it's 1. If it's 0, you're random. You did a very crappy job. You're not doing that good, and it's basically when you're saying something, nobody can really trust you. If you're getting -1, what does it mean? It means that you did the worst as possible. Each time that you said it was positive, it was really negative, and vice versa. It's just like It's just like those get being wrong all the time. So this is the correlation. If we're talking about the geometry meaning of the Matthews, if you did a good job, you'll get a perfect square. Otherwise, you get some kind of a paragram. And you can prove, it's not that hard, that this paragram area is bounded by 1. And the only case that you would get 1 is that in a perfect square. It's a little bit, you need to go, it's a little bit, go deep inside the details, a little bit digging, but it's possible to prove it. So this is what a math correlation tells you. And the nice thing that you need to notice that you don't care about positive or negative, and it's about the positive and negative, the classes. And if you're interested in this stuff, the math correlation is considered to be a better metric than F1. There's a few papers about that, but that's about it. So I think I made things a little bit more clear now. If otherwise, let me know. Okay, let's continue. Okay, in the multi-class, we want predicted for multi-class. We want, again, bounded by 1 and -1. We want things to be.
Before you want to remind them of an example of the multi-class. Give them an example.
Okay, let's go about the multi-class. You're working in e-commerce and your website is selling clothes, so you might, so one class can be shirts, other pants, other ones, I don't know, shoes, socks, coats, towels, bathing suits. So basically, you're having all those classes, and you want to predict which one of those classes your client is interesting. It might be if you're working in cyber, some of those attacks might be very different from to each other. So basically, what do? If you consider all of them as attack and non-attack, it might mislead you because they are very different. So you want to do it in many classes. Maybe you're interested in medicine and diagnostic, and this could be, unfortunately, there's more than one illness that you want to diagnose, and etc. I think is it more clear?
But before you give the illness example, in the case of illnesses, you may have cancer and a heart attack at the same time. So I'm not sure it's the same as what you wanted before.
Well, true. You can do that you can do that, but usually in medicine, and you can have a heart attack and cancer, but usually when people are getting to the hospital, there's the major issue, other heart attack, kidney failure, the major thing, and you want to detect that. And
so so the classes are exclusive. For example, something cannot be both shoes and pants at the same time. There are either shoes. A product cannot be shoes and pants. It's either shoes or pants.
Yeah, this is what we're doing now. And there's some work, especially in computer vision, that you can be both. You can be, someone might purchase a pants and a shirt, which makes sense, but not necessarily. It's not must, but for our purpose, for our machinery, we assume that, and it's so assume that. So basically, what we're interested, first of all, we want to let you to rename your class. If you want to change your illness name or their order, we don't care. The second thing is that something that which is a little bit equivalent to the in statistics, the non-bias predictor. What the non-bias in regression means that sum of your error must be 0. Otherwise, you're biased, and you don't want that. So basically, our equivalence is flipping your predicted and your real value target. So it's a little bit equivalent, not 100%, but we do that. But okay, we can have the general confusion metrics, and which means the ij entry would be how many times you predicted on the class I when it was a class J, just like the regular matrix. Okay, we can always choose the F1 approach, which means that we defined F1I, which would be taking the average, some kind of a harmonic average between the chances of being in real I and you predicted I, and that's basically what we're doing. We're talking, if you think about some kind of a matrix, we're talking about the diagonal, and this is some kind of a trace operator. And of course, everything can be generalized to weighted mean for different kind of average and stuff like that. Go for it. I want to remind you all about the chi-square test. What does it mean? If you get two categorical features, we're testing we're testing the probability dependency. What does it mean, probability dependency? Let's say you have two categorical features. Let's say a state in the US, and if someone is bought which kind of e-commerce, each outfit a company he bought. So basically, if what I'm trying to say, that if I'm telling you that someone is from the state of Texas, he must bought a shirt. If someone is from New York, he bought pants. So basically, this is dependency. And non-dependency, that if I'm telling you that a guy is from some kind of a state in the US, you would have no, it won't help you to construct some kind of predictor that would tell you to get to the better band. So this is, so basically this is, and if you're interested in this approach, the chi-square would give you a good solution. And the Kramer is taking this as some kind of a normalized, we're asking, and basically what are we using? If you're having like this n of n matrix, so basically it tells you, just like in the Matthews, if you're kind of checking correlations. So if I told you that it was predicted positive, you're asking how much it's dependent that real target would be positive. This is one approach. The problem with this approach that you would fail to see that if I predicted to J and J to I, you won't able to see that. Another approach is can we silence this guy? Okay, let's continue. I don't mind. I don't want anyone to stop me and ask question. It's you're welcome, and I'll be happy if you would do that. but this background is a little bit take me out of balance. So basically, we're doing the Matthews. We're just like the previous time. We're defining, instead of 2 by 2, we're taking a matrix of n by n. Is the geometric mean is the chance of being I when you predicted j, and predicted j when you're giving I. The determinant of this n by n matrix is a correlation, and let's remember that determinant is in 2 dimension. It's area. In 3 dimension, it's volume, and 4 dimension and more, it's kind of hypervolume, and which means that how much. And just like in the 2 dimension, we're getting a perfect cube in a perfect predictor. Actually, there's some cases that you can get a perfect square when you're not perfect, but you can spot this right away. And otherwise, you will get some kind of paragram that would be area of less than 1. Okay. Okay, sorry, we went backwards. Okay. So basically, what do we have? I'm about to finish. Don't worry about that. We can take some kind of a F1I. This is one approach. Another approach is a Kramer. Another is a general Matthew correlation, just we mentioned earlier. All against all is just we're taking every 2 classes and getting the score and some kind of average. You might argue that this is kind of related to the general F1, but this is. And Kramer and general Matthews are 2 different ways to generalize the Matthew correlation 2 by 2. Brian Matthews was a biochemist from Australia. Kramer is from Sweden. So this is a little bit, and this is a code. And as about all those stuff, you can see that this code is very simple. I wrote it, so it can't be that hard. And if you're interested, we're having a PyPy library. You can pip install it. With Yaakov's great help, we're trying to make it to the scikit-learn kit. So hopefully we'll get there. And so basically, let's sum it up. And so we introduced a classifier multi-classes. We made some geometric interpretation. I think the most interesting thing is understanding the geometry, because the geometry and probability kind of linked up, and it's important to to see what's going on. And you can add me on Facebook, LinkedIn, Twitter, whatever. Email me, and if anyone has question, I'll be happy to answer. And okay, here I am.
Hey, thank you so much, Uri. All right, so nice to have everybody in the same room so I can hear the claps at the same time. Nice. Well, thanks so much. Are there any questions or?
So let me lead up with a question to give some idea. So you're showing us an example with all those scores. It's something that's been using for years in binary problems, meaning yes, no, or 1-class problems, basically. Now you're telling us, oh, you cannot use those metrics to figure out whether your model is correct when you have multiple classes, or if you do, then you lose something.
Well, actually, you couldn't do that.
Okay, my question is, you'll explain why you can do this. This is the first part. The second part is that I'm interested in saying, what if I have a problem where I have many instead of a multi-class, what if I take a binary case and I just say I have, instead of 5 classes, I have 2 classes? What does this a new metric, what does it become? Does it become an F1 score?
The F, okay. First of all, if you would use scikit-learn in a non-binary cases, it would give you an error. So basically, you couldn't do that. So
there was no Python function off the shelf that I could use that will give me this method.
Well, there was, I think in the scikit-learn would give you an error. Otherwise, they would do, like, they would choose one class, the 0 class, and decided that it wants against all this class. If you want to use if you want to distinguish, you have, let's say, 3 classes, 0, 1, or 2, and you want to distinguish 1 or 2, your metric would never give that. So basically, till this point, the machinery was not there. And for your second question, what would happen if I'm planning for an n by n for n classes, but eventually n is equal to? The answer is I'll get exactly what would happen otherwise. Like the Matthews would be a 2 by 2 Matthews. Kramer as well. The all against all would be just the same. The F1 would be the F1. It's called, I think it's called kind of symmetric F1. So everything would be just cool and fine if you're using more than 1 classes. So basically the...
But is it the same like as the F1 score?
Not exactly. The F1 score, you focus on the positive. You're not focusing on the negative, but you do have something which is called some kind of a symmetric F1, which means that you're averaging the F1 of the recall and the precision and the F1 of the specificity and the NPV, which means that you're focusing on the positive and then on the negative, and then somehow you're averaging things up.
So you're telling me this Matthews converges to this special case that you're averaging the recall and...
Matthew would converge to the 2 by 2 Matthews. There's a 2 by 2 Matthews that was introduced by Brian Matthews in Australia. I think it was in Australia. Later on, he immigrated to the UK, but he's Australian. And if you're using 2 by 2, you would get exactly Matthew correlation. Matthew correlation is implemented in scikit-learn in every, it's one of those classics metrics. So basically, I would converge to the regular Matthews. Otherwise, the reason we choose to generalize the Matthews and not kind of F1, because the standard F1 cannot be generalized since you're giving the positive more attention. And then you need to take the symmetric, but the symmetric is not used as often as the non-symmetric. And however, when you're using Matthews, it's plain, would be plain sailing.
Okay, so before, unless someone has any more questions, because you already led to this, basically what you're telling us that currently the current Python tools that we have available do not have the tooling necessary for multi-class, that you want to have proper scoring and evaluate your model properly in multi-class with multi-class domain. But it has the tools for binary domain, the library that you pointed out that you can pip install, can you see, show the page with the pip install? This, if you pip install this, then you will have the necessary functions that will allow you to actually evaluate your model properly. This is what
exactly.
you're telling me.
Yes, exactly. If you're doing this pip install function, you can use our function, which this is basically the code, and you would get you would get a metric for multi-class, and you're good. Right now, we're in a kind of a process, since you're involved, you probably know it as well. We try to do it inside of scikit-learn. So basically, our approach is that if you're doing scikit-learn and you're using it with multi-class, it would give you the multi-class score. But I think there should be some kind of a warning, because in many cases people are not aware that they're using more than 2 classes, because people are just, it's so built in that it's commonly, and people using the 2 classes because everybody's doing that. And then if someone is doing multi-class, it's some kind of non-standard thing.
Okay, so now it's a call, and basically you are telling us you want to include it in some bigger library like scikit-learn or SciPy or whatever. Austin is a good place for this, because a lot of those mathematical libraries originated in Austin, like NumPy and SciPy. Those are, a lot of them originated in Austin. So people in the audience may know someone who knows someone that can help you. So if someone knows in the audience, in the room, knows people who are affiliated with scikit-learn, SciPy, please let them know, and hopefully those functions will get into some open source library that is more useful, more in use, not useful.
Yeah, okay. Okay, so basically this is what I'm going to tell you. Any question, except for Jacob, just go ahead. If you're shy, you can contact me this way, and I'm done here. So thank you for listening.